Good morning everyone, myself Sanskruti Pampattiwar and I am here to give the presentation for predictive analysis, and today we will be going to cover the topics or the techniques related to artificial neural network, that is ANN. So let's start. Let's start with the introduction. Introduction. Deep learning is a subfield of machine learning that involves building artificial neural network and multiple layers. These neural networks are modeled after the structure of human brain, and they are capable of learning from large amount of data to make predictions, recognize patterns and perform other tasks. Deep learning has become increasingly popular in recent years due to its success in a wide range of applications, including image recognition, natural language processing, speech recognition, and even gameplay. This success is largely due to the ability of deep learning algorithms to automatically learn features from raw data, allowing them to handle complex tasks with high accuracy. Now let's see what is CNN. CNN is a convolutional neural network, which is a type of neural network that is commonly used for image and video recognition, classification and segmentation tasks. It is composed of several layers, including convolutional layers, pooling layers, and fully connected layers. The convolutional layers are responsible for detecting features in an input image. These layers use filter, also known as kernels or weights, to scan the input image and extract relevant features such as edges, corners, or blobs. The output of the convolutional layer is a feature map that highlights the presence of these features in the input image. The pooling layers are used to downsample the feature map and reduce the spatial size of the data. This helps to reduce the number of parameters in the model and make it more efficient. The most common pooling operation is max pooling, which selects the maximum value in each pooling window. This helps to reduce the number of parameters in the model and make it more efficient. The most common pooling operation is max pooling, which selects the maximum value in each pooling window. The fully connected layers are responsible for making the final classification decision based on the extracted features. These layers take the flattened output of the previous layers and perform a classification task, typically using a softmax activation function. CNNs have been shown to be very effective for image recognition tasks such as object detection and classification, and have been used in a wide range of applications including self-driving cars, facial recognition, and medical image analysis. Next comes RNN. So what is RNN? RNN is a recurrent neural network, which is also a type of neural network that is commonly used for sequence modeling tasks such as speech recognition, natural language processing, and time series prediction. Unlike feed-forward neural networks, RNNs have connection between neurons that allow information to flow in a loop, allowing them to capture the temporal dependencies of sequential data. The key feature of RNN is the presence of hidden state that is updated at each time step and used to capture information from previous inputs in the sequence. This hidden state acts as a memory that stores information about the past inputs and influences the computation of the current output. RNN can be trained using backpropagation through time, a variant of the backpropagation algorithm that is used to update the weights of the network based on the error signal propagated back through time. One of the challenges of using RNN is the vanishing gradient problem, which can occur when the gradient of the loss function with respect to the parameters of the network become very small, making it difficult to train the network effectively. To address this issue, several variants of RNN have been developed, including long short-term memory network and gated recurrent units, which use specialized gates to control the flow of information through the neural network and prevent the gradients from vanishing. RNN have been shown to be very effective for sequence modeling tasks such as language translation, speech recognition, sentiment analysis, and have been used in a wide range of applications including chatbot recommendation system and predictive text input. Next is autoencoder. So what is autoencoder? Autoencoder is a type of artificial neural network that is commonly used for unsupervised learning tasks such as data compression, feature extraction, and anomaly detection. The basic architecture of an autoencoder consists of two parts, encoder and a decoder. The encoder takes the input data and compresses it into lower dimensional representation, which is then fed into the decoder to reconstruct the original input data. The encoder and decoder are typically implemented as neural network with several layers of nodes, allowing the autoencoder to learn complex relationships in the data. During training, the autoencoder learns to minimize the difference between the original input data and the reconstructed output data. This is typically done by minimizing the mean squared error between the input and output data. Once the autoencoder is trained, the encoder network can be used to extract features from new data, and the decoder network can be used to reconstruct the original data from the compressed representation. Autoencoders have many applications in image and signal processing, natural language processing, and anomaly detection. They are also used as building block for more complex models such as variational autoencoders and generative adversarial networks. Here is a pictorial representation of the structure or the architecture of the autoencoder, which consists of encoder and a decoder. Next is deep belief network. Deep belief networks are a type of artificial neural networks that are used for unsupervised learning tasks such as feature extraction and data compression. DBNs are composed of multiple layers of restricted Boltzmann machines, which are a type of generative sourced artificial neural network. The RBM is a DBN. DBN is a short form of deep belief network, which are trained layer by layer in an unsupervised manner using a technique called contrastive divergence. During training, the lower layer learn to extract simple features from the input data, and the higher layers learn to extract more abstract features by combining the features learned in the lower layers. Once the RBMs have been trained, the entire DBN can be fine-tuned using a supervised learning algorithm such as backpropagation. The fine-tuning process adjusts the weight of the connection between the layers to minimize the error between the DBN's output and the target output. DBNs have many applications in fields such as computer vision, speech recognition, natural language processing. They are especially useful in situations where the amount of labeled data is limited, as they can be pre-trained on large amount of unlabeled data to learn useful features that can be then used for supervised learning tasks. Next comes restricted Boltzmann machine, which is RBM. It is also a type of artificial neural network that is used for unsupervised learning tasks such as feature extraction, dimensionality prediction, and data compression. It is a type of generative stochastic artificial neural network that is typically composed of two layers, a visible layer and a hidden layer. The visible layer represents the input data, whereas the hidden layer represents the learned features. The connection between the layers have no direct feedback, and the RBM is trained using a technique called contrastive divergence. During training, the RBM learns to model the probability distribution of the input data. This is done by adjusting the weights of the connection between the visible and the hidden layers to maximize the likelihood of the training data. Once the RBM have been trained, it can be used for a variety of tasks such as image and speech recognition, recommendation system, and anomaly detection. One of the main advantages of RBM is that they can be used to learn useful features from unlabeled data, which can then be used for supervised learning tasks. RBM can also be started to form deep belief network, which are a type of multi-layer neural network that can learn increasingly complex features by combining the features learned in each layer. RBM have been used in many applications such as computer vision, natural language processing, and speech recognition. They are also used as a building block for more complex models such as deep neural network and generative adversarial network. Next come GAN, that is generative adversarial network. Generative adversarial networks are a type of artificial neural networks that are used for generative modeling tasks such as image and text generation. GANs consist of two neural networks, a generator network and a discriminator network. The generator network generates fake data such as images based on a random noise input. The discriminator network, on the other hand, learns to distinguish between the fake data generated by the generator network and the real data from the training set. The two networks are trained together in a two-player minimax game. The generator network is trained to produce fake data that is as close as possible to the real data, while the discriminator network is trained to correctly classify the fake and real data. As the two networks are trained together, the generator network improves its ability to produce more realistic fake data, while the discriminator network improves its ability to distinguish between fake and real data. Eventually, the generator network produces data that is indistinguishable from the real data. GANs have many applications such as generating realistic images, synthesizing text and generating music. They have also been used in domains such as computer vision, natural language processing, and drug discovery. One of the challenges of using GAN is that they can be difficult to train and can suffer from problems such as node collapse, where the generated network produces a limited range of output. However, recent advancement in GAN architecture and training techniques have addressed many of these challenges, and GANs continue to be an active area of research in ML. Next is transformer. A transformer is a type of neural network architecture designed for natural language processing tasks. It was introduced in a paper by Vaswani et al. In 2017 and quickly became one of the most popular and effective architectures for natural language processing. The key innovation of the transformer is the self-attention mechanism, which allows the network to weigh the importance of different words in a sentence when processing it. Unlike traditional recurrent neural networks, the transformer is designed to be parallelized and can process input sequences in parallel, making it much faster and more efficient. The transformer has been used in a variety of NLP tasks, including language modeling, machine translation, text classification, and sentiment analysis. It has also been adapted for other domains such as image processing and speech recognition. Next is ResNet. ResNet is a short form for residual network, which is also a type of deep neural network architecture that was introduced by Microsoft Research in 2015. The key innovation of ResNet is the use of residual connection, which allows for the training of much deeper neural network that was previously possible. In traditional neural network, each layer learns to transform the input data into a higher level representation. However, as the network gets deeper, the gradient data backpropagated during training become very small, making it difficult to learn meaningful features. Problem is known as the vanishing gradient problem. Residual network addresses the vanishing gradient problem by introducing residual connections, which allow the network to learn residual functions that are added to the output of the previous layer. This means that each layer only needs to learn a small residual function rather than trying to learn the full transformation from the input. ResNet has been widely adopted in many computer vision tasks such as image classification, object detection, and segmentation. It has also been used in other domains such as speech recognition, natural language processing. ResNet has several variants such as ResNet 50, ResNet 101, ResNet 152, which differ in the number of layers and parameters. These models have achieved state-of-the-art performance on various benchmarks and widely used in research and industry. Next is long short-term memory networks. Long short-term memory (LSTM) is a type of recurrent neural network architecture that is designed to overcome the problems of vanishing and exploding gradients that are often encountered when training traditional RNNs. LSTM are particularly well suited for processing sequential data such as natural language text, speech, or time series data because they are able to remember long-term dependencies between input sequences. LSTM achieve this by using a series of gating mechanisms that regulate the flow of information through the network. The core component of an LSTM cell is the memory cell, which stores information over time. The cell can also have three gating mechanisms that control the flow of information: the input gate, forget gate, and the output gate. The input gate controls which information should be stored in the memory cell, the forget gate controls which information should be forgotten, and the output gate controls which information should be outputted from the cell. LSTM have been used in a wide range of applications, including natural language processing, speech recognition, image captioning, and predictive modeling. They have proved to be particularly effective in tasks that involve long-term dependencies such as language translation and speech recognition. Radial Basic Function Network. Radial Basis Function Network are a type of artificial neural network that use radial basis function as activation function. RBF networks are commonly used for function approximation, classification, and pattern recognition tasks. In an RBF network, the input layer consists of the input neurons which receive the input data. The hidden layer contains radial basis neurons which use radial basis functions as activation function. The output layer consists of the output neurons which produce the output of the network. Radial basis functions are mathematical functions that are centered at the certain point and decreases in value as the distance from that point increases. The most commonly used radial basis function is the Gaussian function, which has a bell-shaped curve centered at a center point. During the training phase, the centers and the widths of the radial basis functions are determined using a clustering algorithm such as k-means clustering. The weights between the hidden and output layer are then trained using supervised learning techniques such as backpropagation. RBF networks have several advantages over other types of neural networks, such as their ability to handle noisy and incomplete data and their ability to learn quickly and efficiently. They have been used in a wide range of applications, including financial forecasting, image classification, and speech recognition. So here below given is a diagram for that, which shows input layer, hidden layer, and output layer. Next is reinforcement learning. Reinforcement learning is a type of machine learning that invokes an agent interacting with an environment to learn how to perform a task. The agent learns through trial and error by receiving feedback in the form of rewards or punishments for its action. Reinforcement learning has been successfully applied in a wide range of domains, including robotics, game playing, and autonomous driving. In a reinforcement learning problem, the agent takes action in an environment based on its current state. The environment then responds with a new state and a reward signal which indicates how good or bad the agent's action was. The goal of the agent is to learn a policy that maps states to action in a way that maximizes the cumulative rewards over time. One of the key challenges in reinforcement learning is the exploitation trade-off. The agent must explore the environment to discover new potentially better actions while also exploiting the knowledge it has already gained to maximize its reward. There are several different algorithms used in reinforcement learning, including value-based methods, policy-based methods, and actor-critic methods. Value-based methods such as Q-learning learn the optimal value function for each state action policy pair. Policy-based methods such as policy gradient methods learn a probability distribution over actions given the current state. Actor-critic methods combine both value-based and policy-based approaches by using an actor to choose actions and a critic to estimate the value function. Reinforcement learning has been used to solve a variety of complex tools such as playing games like Go and chess, controlling robots, and optimizing energy consumption in data centers. However, it also has limitations such as the need for large amounts of data and the difficulty in dealing with continuous state and action spaces. Next is self-organizing maps, or SOM, are a type of artificial neural network that can be used for unsupervised learning and visualization of high dimensional data. SOMs were introduced by Theo Cohen in 1980 and are also known as Cohenian maps. SOM consists of a grid of neurons where each neuron represents a cluster of similar input data points. The neurons are connected to each other and the connections are weighted. During the training process, the SOM adjusts its weights based on the input data to create a topological map of the input space. The training process involves presenting the input data to the SOM and then updating the weights of the neurons to make them better match the input data. The update process involves finding the neurons with the closest weight vector to the input data and updating the weights of the nearby neurons based on a learning rate and a neighborhood function. This process is repeated multiple times until the SOM has converged to a stable state. SOMs can be used for a variety of tasks such as clustering, visualization, and dimensionality reduction. In clustering, the SOM can be used to identify similar groups of data points which can be further analyzed. In visualization, the SOM can be used to map high-dimensional data to a two-dimensional grid, making it easier to understand and interpret. In dimensionality reduction, the SOM can be used to reduce the dimensionality of the input data while preserving the structure of the data. SOM have been applied in many domains including image and speech recognition, data mining, and bioinformatics. They are particularly useful when dealing with large and complex datasets where traditional clustering and visualization techniques may not be effective. Then Hopfield network. Hopfield networks are a type of artificial neural network that are used for pattern recognition and optimization problems. Hopfield networks were introduced by John Hopfield in 1982 and are based on the concept of energy minimization. Hopfield networks are made up of set of neurons that are fully connected to each other, forming a recurrent network. Each neuron can take on one of two states, either on or off, which can be represented as binary values of 1 and -1 respectively. The connections between the neurons in a Hopfield network are symmetric and have weights that are determined by the correlations between the pattern that the network is trained on. The weight matrix is trained using the Hebbian learning rule, which strengthens the connections between neurons that are activated together. During operation, a pattern is presented to the network by setting the states of the neurons to the values of the pattern. The network then iteratively updates the state of the neurons until it converges to a stable state. The update process involves computing the activation of each neuron based on its input and the weights of the connection to other neurons. The activation is then thresholded to produce the new state of the neuron. Hopfield networks can be used to perform pattern recognition tasks where the network is trained to recognize a set of patterns and then retrieve them from partial or noisy inputs. They can also be used to solve optimization problems where the network is trained to minimize an energy function that represents the problem. Hopfield networks have been applied in a variety of domains including image and speech recognition, constant satisfaction, and optimization. However, they have small limitations such as the fact that they can only store a limited amount of patterns and the fact that they are sensitive to noise and can stuck in local minima. Next is associative memory network. An associative memory network is a type of neural network that is designed to learn and store associations between different pieces of information. It is a type of neural network architecture that is particularly well suited to tasks that involve pattern recognition, classification, and prediction. The basic idea behind an association memory network is to create a set of connections between different nodes in the network, where each node represents a particular feature or characteristics of the input data. These connections are then used to represent the associations between different pieces of information. During training, the network is presented with a set of input data along with the associated output data. The network learns to associate the input data with the correct output data by adjusting the strengths of the connections between the nodes. Once the network have been trained, it can be used to make predictions or classifications based on new input data. The network will activate the nodes that are associated with the input data and then use the strength of the connection between these nodes to make a prediction about the output data. Associative memory networks have been used in a variety of applications including image recognition, speech recognition, natural language processing, and robotics. They are particularly useful in situations where there is a large amount of complex data to be processed and where there are many possible associations between different pieces of information. Thank you.